Good morning, everyone. So as usual, we will have our quiz starting 11:10. So please be ready to start as soon as it opens, and you will have 15 minutes to finish it. Any questions before we, related to the quiz or to this tutorial? Okay, I will respond to questions in chat when they arrive. And we will start the quiz in 8 minutes. After the quiz is over, please, come back here and we will cover some material we were not able to finish properly in our tutorial, mostly about comparators. And I show a couple of training questions for you as well. After that's done, people that would need my assistance, we would hold in office hours right after we're done. Okay, you should be able to start the quiz now. Good luck. And there is this general question that's keep coming, what the quiz is covered. And the short answer is it can have all the material that was presented in the lectures before that. Hi guys, we will start the lecture in a few minutes. I'm just waiting a few more people to finish. Okay, can everyone hear me well? Okay, please guys, we will discuss the quiz afterwards and you'll get the correct questions at 11:40, so you can look at what you did wrong or not. I tended to check everything this time, so I think it should be fine. By just looking at the average, if you're curious, I think it's 69 or 70. Like after everyone finished, I will tell you precisely, but it's around 70. Also had around 10 or more people who got 100%, which means it was a legitimate, test. Although, yes, the came-ups question at the beginning may take some time, but the other questions were simpler in terms of how much time you need to spend on them. Okay, so the main purpose of today's tutorial is first quickly finish what we didn't finish at the lecture. So some part of the comparators. As usual, I ask if some of you can turn on your camera. That would be amazing. So I can see both your questions and your faces. We try to make the quiz interesting, so some questions were just, straightforward from the lecture, some you need to think, but all the materials that were needed to answer those questions was literally in the lectures, so there's nothing extra you would need to read to answer those. Okay, if you're not sure about something, you can post questions on Piazza and one of the students will respond and one of the TAs or me will respond to that. Okay, let's now talk about comparators. So what I covered in the lecture today, I talk about multiplexers, demultiplexers, right? I show you the design. I show you several examples. We also did some stuff with decoders and coders where you would see, multi-input stuff. So should help you with one of the questions in this test. I think a lot of people got it right. We also spent a lot of time on adders and subtractors. This was, especially the adders design was a more advanced topic. So we didn't put questions on it in the quiz. So essentially that will be covered more in the next quiz, right? We had one question on subtractors, obviously, but that was more like not design of the subtractors, really was more like a basic questions around it. And today we want to finish comparators. Again, right now I'll just remind you what we covered in the lecture. This is essentially comparator is a very simple circuit in a sense. It's something, if you ever use assembly language or even C language, this is essentially the condition of an if statement. You are just trying to compare two input vectors and determine if the first value is greater than or equal to the second one. So we look at how to build this circuit, right? And obviously similar to adder, we started with 1-bit cases. So this is essentially the input, part of the input truth table. And then for A equals B, if you want to build a truth table, it's essentially very simple. It's you either need to have 2 ones or 2 zeros. That's essentially what the formula here reflects. This is A bigger than B, and this is A smaller than B, right? They had a very simple formulas. So obviously the comparator for that will be just a circuit that would join these 2 inputs with 3 outputs, right? And obviously we don't want to have 3 different comparators, so we'll build them all in one design to save on circuits. So as you move into more and more complicated stuff, so even if you start to look at 2-bit, you would see that the term required for this circuit becomes more and more complicated. And again, one thing, I'm going to show you how it looks for 2-bit. I already shown in the lecture, I'll show again and explain. But one thing you want to understand is that complexity in terms of design doesn't mean complexity in poor latency, right? Something might be difficult to design but have amazing latency, or vice versa. So the trivial solution for comparators is to do subtraction and then compare that with 0, right? Or just look at the sign bit, right, essentially. But that doesn't mean the optimal. It's easy to engineer, but not necessarily the fastest. So essentially the way we build A equals B, we make one term, right? Make sure that the values of bit 1 are the same, right? And there is a second condition that ensures that the values of bit 0 are the same. So what this means, so if you want to make a condition that the first bit is the same, you say either both first bits are 1 or both, this is or, right? Or the both first bits are zeros. This is literally that, right? So this is to make sure that the values of the bit 1 are the same and the values of the bit 0 needs to be the same. And that's the condition for that. So this is literally how we write this circuit, right? But this is only one output of that circuit. It's A equal B. Things get more complicated when you want to make A bigger B, because the way we compare vectors, you've probably seen this from calculus, right? When we compare multi-variable functions, we need to do it dimension by dimension, right? So here for 2 values, when we have 2 inputs, 2-bit inputs for A and 2-bit inputs for B, first you start to compare the leading values, right? The leading values are relatively straightforward. If A is bigger than B, so A1 is 1 and B1 is 0, you're done. There's no need to look for other bits. So that's one condition. And this is the second condition. If they happen to be the same, so the same, what really means to be, what really means to be the same, right? The same means that it's either both ones or both zeros. If that happens, then if that's true, we can look for the last bit, and the last bit A0 should be bigger than B0. So A0 is 1, B0 is 0, right? This is pretty much what these formulas do for you, right? And A less than B is essentially the opposite conditions. Okay, is this clear to everyone how the comparators would be built for 2-bit? Any questions here? Lost. I don't see anyone responding. So guys, is this clear? Okay, thanks, Sam. So yeah, so that's, I still just repeat what I covered in the lecture, right? This is not really new material. So essentially, the rest is, if you're curious how you would build it in a more general case, then the case of equality is relatively straightforward, right? You just have xi, each essentially case defined this way, right? So you would be comparing each bit, each digit I independently. So you say that it's either both ones or both zeros. So the equations is very simple. A equals B is x0 and x1 and xn, right? So this means if your input is n, so here's from 0 to n, it means n plus 1 digits were entered as an input, and xi is essentially checks whether the digits are identical, both zeros or both ones. So the equality case is simple. As you can see, you can just literally build a straightforward circuit like that. But A bigger than B, A smaller than B becomes quite complicated, as you can see. So essentially, you would need to do what we do for 2 bits, but kind of recursively. So you first compare the leading bit, right? AN bigger than BN, right? So this is 1, this is 0, that means A is bigger than B. Then if it's not the case, you need to write a conditions saying that essentially they're equal. So you would need to use xn here, right? And then you need to write, all the pairs of, the next bit. The next bit is equal. So it's essentially first you compare the leading bit, Then you compare, if the first two beats are equal, then you compare the next pre-last beat and so on. And this is the tail here. So as you can see, that becomes very complicated at the end. So this is how the truth table will look like for just a case of n equals 2, right? And I'll just show you very briefly how you can, build, using our favorite technique, K-maps, how we can build a circuit for it. So you see, this is what we get. So we get this 4 here, and we get this pair and this pair. And this is essentially less than circuit is going to consist from 3 terms, right? Again, you can do it at home. So the truth table is on the previous slide. It's relatively straightforward, right? You can just do it. It's just tedious process. So I just put it all for you here, right? As you notice, we're not asking you to do this by hand for large tables because that's time consuming, but you get, the idea. And K-maps, you can see, you can be very powerful to get an optimal formula for that, right? Doing this manually, you already feel how much energy you would have to spend, right? K-maps is very powerful technique to do it. So similarly, we can do A equals B, right? You see they all 4 terms are like that. So there's nothing really fancy you can do. Each of them, this is really just an X term, X1 term. And A bigger than B is symmetrical, so also how greater is, has in 3 terms as well. Okay, and as I said, for the practical purposes, when the design becomes way too complex, right? At some point, you may just say, you know what? I would rather sacrifice the efficiency of circuit a little bit for the ease of design, so that people, instead of doing something like that, doing just subtraction and check for the sign bit. Okay, but just remember, simplicity of their work for you doesn't mean better circuit. It's still probably going to be less efficient, right? But at some point, debugging those circuits becomes a nightmare in Verilog. Okay, any questions, guys? This is kind of concludes the lecture on this basic circuits, right? So next week, we're gonna talk about memory. So I kind of taught you by now at how to do basic logic. We started, with the basic gates, then we learned how to do AND OR. Then after that, we learned how to do AND subtraction comparators. You can see you can already write a simple program using this mechanism, using Logisim or Verilog. But I still didn't show you how to store stuff. Remember, to compute, we had 2 big pieces. We need to execute instructions, but also want to store data, right? So in the next lecture, we're going to talk about how the memory is organized, how you store values there. Any questions? So Sam is asking, could you do A minus B as negation of the other 2? Yes, you can. In practice, I'm simplifying things. Like when you're going to use assembly, there are going to be other instructions like a less or equal or greater than equal, right? So it's just, it's definitely possible to do it, but remember the fact that you had an easier math to write here, like not of something, it doesn't mean that it's faster in terms of execution. For example, think about it, Sam, what you wrote here. I think everyone can see the question, right, in the chat. So the question is essentially, can I use, instead of doing A bigger than B, I just use the negation of the other 2. So on the, if you think about the amount of hardware you need, you might save a little bit. But in terms of latency, you will lose. Why? Because you would have to do the other 2 and then do a NOT of it. So the latency would be worse, actually, right? You would have to go through a longer critical path. So this is a perfect example. I like the question because it's a perfect example of a trade-off in the design, right? You might spend more hardware, right, to make it faster, but you make, to spend on area, save on area, so use less gates, less transistors, but it may take longer latency. So at this basic level, like add or like the basic AND, like those instructions are so critical for latency. So usually the choice of engineers goes into the latency first, because the area is still not as critical at this level. But eventually things will get complicated. So for example, when we're going to talk about memory, there sometimes the simplicity of design and making sure that you're really very efficient in terms of density dictates you to go for simplicity rather than speed, right? But for arithmetic units like add, comparison, you always go for speed in most cases. Okay, any other questions? Okay, so I'll just show you a couple of questions here that should you just kind of prepare for future quizzes and just practice on things we did on this quiz as well. So for example, in the interest of time, I'm going to show you the answers, but I'm going to give you some time to practice as well. So the first question is, how do you write the number 78 as an 8-bit binary number? So please try it out yourself. So that's a good practice. And then you see the other, two questions. I'll give you a few minutes. Please try to do all 3 questions yourself, and then you show the correct answer. So it kind of forces you to try it out on your own. And yes, I know you're all smart. You can use scientific calculators. You can use, apps for that. But please try to do it by hand as well, so you understand it better. And give everyone this few minutes, so don't type the correct answers yet. Just wait at least for a few minutes so everyone can give it a try. Okay, I think people who are ready, you can type your answers for A. So for everyone, I'll just explain. So what happens? So 8-bit binary number, it means you have positions of different powers of 2 from 2 power 0, which is 1, all the way to 2 power 7, which is 128, right? So essentially, what we're going to do, we're going to look at which powers you need to build 78. So the biggest is 64, then 32 would be too much, 16 would be too much, then it's 8, 4, and 2, right? So it's 0, 1, 0, 0, 1, 1, 1, 0, okay? So 2's complement, right? 2's complement is also very straightforward, right? You take this value and first compute 1's complement, which is you just negate all the bits, right? So you're going to get essentially 1, 0, 0, 1, 0, 0, 1, 0. And then to get 2's complement, I need to add another 1. And that another one converts the 0 into 1, right? That's how you get 2's complement. And the 2's complement is essentially the negation, right? And what is the sum of this value and this value? So again, this is usually a straightforward process. You put them one by one, add them up, right? And make sure you properly handle the carry. So you can now check on what you did. Any questions here? Okay. Another question on K-maps. You probably noticed that K-maps is very important. And here we're handling the case where there are undefined inputs. So this is the K-maps where we have some axes in it. So what I want you to try out here, either on the piece of paper or just visually, I think on the piece of paper would be better, is find the right groupings for the K-map on the right. And then after you do that, try to write the logic equations to do these groupings. I'll give everyone at least a minute, so please try, and then I'll show the answer. Are there any questions, guys, about this? Okay, I think I gave you enough time for the first one at least, right? So you see here, that's the first thing you do. You try to get the massive one, right? So to get the massive one, you want to get all the ones, right? So you get pretty much half of the table here, right, covered. Then another one, this long horizontal lines, right, this, right? So how it's going to be reflected in the math. So essentially, when I collapse the half of the table, it really means that all these variables, A, B, completely irrelevant, and so is D is irrelevant. So when I look at what this half of the table generates, it just generates one term, not C, right? Because only C, not C matters. And then essentially, then you look at this, this was two vertical lines, man. And this horizontal line generates a term, not A and B, right? Because all it's once across all this term, right? And everything else is irrelevant. Does it make sense to everyone? So you can see how manipulating axes, we can make the circuits much simpler, right? And those undefined cases are actually quite common because very frequently you would going to use it, you know, binary number of inputs, but binary encoding, right? But the number of real inputs to cover you is definitely less than that. So you're always going to get with some excess, right? Undefined cases. Okay, this is pretty much what I have for today. So any questions to what I presented? So we covered everything we need to cover for this week. I show you a few questions. One option, obviously, we could talk about the quiz right now, but I would prefer that before you go for questions, right, try to, knowing now the answers and what you did, try to do it by yourself. Don't ask others. First, try to figure it out it yourself. If you can't, then go to Piazza and ask questions, right? And if after that you can figure out, you can talk to me. But I mean, please put some effort first to figure it out, because the goal here is, again, not to test you for grade, making sure you get it, right? Some questions were straightforward, some were a little bit tricky, right? For example, the questions, I think the questions where we did, we compute the, you know, the binary representation of -6, right? It was intentional that I have to, there were two answers that are correct, right? We explicitly didn't specify how many bits you're supposed to use. So there are two correct answers there, not one. A lot of people got the first correct answer because it's kind of straightforward, but the second one, if you think a little bit about it, you understand why it's correct, right? So it also shows you an important thing is that depending on your precision, 8-bit, 16-bit, 32-bit, the -6 in a binary format might look different. In positive numbers always look very similar because they had a lot of leading zeros, so it looks like it's identical, doesn't matter. But the negative ones has a lot of leading ones, right? And so they look different. Okay, any other questions? Chat. Okay, sorry, there are some questions here. Let me look. So we can do the K-map without grouping the axes. I mean, that would be less efficient. Yeah, I think Krutik already responded to that. You can always do it, but you're going to get much more complicated logic, right? Because you're going to assume that x is 0, when in practice it can be 0, 1. Okay, someone asking, was question 3 in the lecture notes? I don't remember all the questions by numbers, to be honest. But everything that was in the quiz was in the lecture notes. So there was literally everything covered. I think question 3 was about multiplexers, right? If I remember correctly. So if it was about multiplexers, so the short answer, there was no exact answer on the slides. I show you how to do multiplexer for 2 inputs. And then I show you how to do decoders for multiple inputs. So you should have compiled these 2 bits of information and get like how to do more complicated multiplexers. So, and intentionally to help you, I asked the TA to put a figure there of 4-to-1 multiplexer there to help, right? So you would visualize it better. And I think majority of people get this question right. So, I don't think there were a lot of issues with that. Yeah. Okay, any more questions? So for the lab, it's better to ask our TAs because they're grading them. So I don't want to answer questions, not to lie you, right? So I didn't look carefully at lab 3 myself yet. So if you're not sure something about the lab, just go to Piazza. They would be more competent to answer the question first. If they cannot answer your questions, that I will help, right? That's what we usually do. Okay, so that's good feedback. Next time we'll try to, I think it was, Quarkus is not always friendly for certain things, but yeah, I got it. We will, like if I had future K-maps questions, I'll tell the TAs to write it in these notations. I hope, again, K-maps questions were answered so well by majority of you. So I was looking for a while, like the correct answer were given by 80-something% of people, right? So I think most people got it. Right, but if it helps, we can use this notation as well. Okay, any more questions? Okay, if there are no more questions, essentially we switch to the office hours mode. So thanks everyone for being in this tutorial today, taking the quiz. People who want to stay and get some questions asked in the office hours, please stay online, and also tell me in the chat that you want to have a one-on-one questions. I'm gonna put you essentially into breakout rooms, so you can talk with me one-on-one. I will try to handle you one by one, right? But like first, I'll let everyone who doesn't have any questions to leave. Thank you guys, and only if you really have a question, stay on the line and also put your name in the chat. So let me know that you want to see me one-on-one with some questions. Yeah, thank you guys. Thanks a lot. As usual, remember I mentioned if you had any feedback on how their course goes in the last 3 weeks, please send us email either anonymously or personally and tell us what you want to improve, so on. Thank you.
Hello, Professor.